Hello, it's Keith here, and this is lesson 91 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at the Amstrad CPC, and we're looking at MaxTile, which is my software tilemap system. It's multi-platform, it's software on this system, but it uses the hardware on a system like the Sega Master System, the ones with the hardware tilemap, but on this system it works as a software tilemap. Now, it allows for scrolling and the movement of simulated sprites. The character moving around the screen is being drawn as a miniature tilemap, and the reason for that is that the same code is doing all of the drawing less to port when you're porting to multiple systems. Now, the tricky thing about MaxTile and what makes it better than MinTile is it has more functionality, and that functionality is optimized for the platform. So it can do things like Xflip the sprites and Yflip the sprites, and it does so in an efficient way for each system, and the way it does it depends on the capabilities and limitations of the system. It also has things like Fastfill sprite tiles. Now you can see here these tiles. These are solid fills or checkerboard fills. Now basically there's a piece of code that's optimized to just fill tiles that are one solid color. There's also an optimized routine for transparency. These are not transparent sprites, although there are parts of this that are not being drawn, but those are whole tiles. This character, however, is using something known, I refer to as 0 byte transparency, and that's where all the bits in a byte are 0. That byte is simply not drawn to the screen, and this gives a very crude but efficient drawing of a transparent effect for sprites where you don't want an ugly border. The ugly border is faster though, which is why we have both options. So MaxTile, as I say, it's designed to give a lot more functionality than MinTile. It's designed to be reasonably efficient for the systems, so the performance is fairly good considering the amount of data being transferred, but it's also designed to be easily portable to multiple systems, and this example will run on a lot of different systems because of the platform-specific driver and the way it was designed to work with common limitations. Anyway, that's what we're going to be looking at. We're going to look at this in two parts because it's quite a big piece of code. So we're going to start by looking this time at the basic code, the platform-specific code for the CPC, and also the main drawing routines for the tiles, the Xflip and the Yflip. And then next time we're going to go into the more unusual drawing routines like the double height and the fast fill, and also we're going to look at the half tile shift version. Now, as I say, that this is heavily optimized to the best of my abilities to work within the drawing limitations of the hardware, and part of that is making sure that we update the HLVRAM destination in the most efficient way possible, not changing both bytes if we only need to change one. The problem is that when we go out of an 8x8 pixel aligned boundary, often that gets difficult on the CPC. Going over the 8 pixel boundary actually requires more calculations, and so I've made two versions of the code, one for when it's aligned to an 8x8 boundary and one with a 4 pixel vertical shift, so you can move half a tile down. Moving half a tile across the screen is easy because each byte contains 4 pixels, so 4 pixel shift is just a 1 byte shift, and the horizontal bytes are perfectly normally aligned. It's the vertical movement in VRAM that is tricky. So anyway, let's go over to the code. Let's see what we've got. Like I say, I apologize for all of that talking, but I needed to explain what we'd actually got today. So this is the first file we'll be going to look at today, CPC MaxTile Mid. This is the example code, the example you saw running, but part of the definitions are in there. The rest of the code is in CPC MaxTile Normal, this file here. That is the actual platform specific tile drawing routine, and if you're not interested in the tilemap, the tile drawing routine will still be interesting because it shows how to do things like Xflip and Yflip in real time, converting the data without having to store a second copy of the patterns. Now, we're using 256 by 192 screen mode, which is smaller than the default, but it makes it more efficient because the HLVRAM destinations are easier to update, take less processing power, so as well as making it more compatible with other systems. A lot of systems are 256 by 192. It also makes it more efficient for us, so it's the obvious choice for this program. Now, to set the screen mode up, we send all of these parameters, these CRTC values, to the CRTC hardware, and we do that basically by this sequence here. Now, here are the register values that are being sent to each of the hardware registers. So the intention is you would use this as is, and this will configure the 256 by 192 screen. Now the screen starts at memory address C000, which is the default for the normal 320 by 200 screen. Strangely enough, the regular screen is 16K thereabouts, and the shrunk screen is also 16K, because the memory layout is quite efficient for us moving around the VRAM. It's quite efficient in that sense. It's not so efficient in the sense of using the memory. There's kind of gaps in the memory that aren't used, and they're just spaces. Now we're actually going to take advantage of some of these. You see, we've got these 512 byte blocks here at these memory addresses, which are simply used for absolutely nothing. And as long as our drawing code is working correctly and is not drawing outside of the visible VRAM, these will be completely free for our use, and so we're going to use them. Now MaxTile itself needs 3 caches because it caches the draws to the 3 strips of the screen, and so it needs 3 256 byte caches, and so we're going to define those in some of those empty areas. That's what we're doing there. And then finally, there's one other thing we need, and that's a 256 byte lookup table for the Xflip effect. That is done in real time, but bit shifting is too slow. So what we're doing is we're creating a 256 byte lookup of all the possible source bytes and the flipped equivalents, and that's how we get the efficiency there. So that's what we've got there. Finally, we've got do EI now. We disable interrupts as part of our running. We're using a stack misuse, which is where we use the stack pointer to quickly read data. Enabling interrupts on this system works fine. On others, it doesn't work so well. So just depending on the system, sometimes I enable interrupts, sometimes I don't. And so I create a macro called do EI, which either contains EI or contains nothing if we don't want to enable interrupts. So just a tweak for the multi-platform code there. So at the start here, we're setting up a dummy interrupt handler. This is just a return so that the operating system interrupt handler doesn't take effect, because it uses the shadow registers, which would cause us trouble, which is a reason we might not want to re-enable interrupts. Anyway, here we're defining the lookup table. Now in screen mode 1, the 4-color mode, each of the pixels uses 2 bits for its 4 colors, and so 1 pixel uses those, 1 pixel uses those, and those, and those. And so what we're doing here is we're taking the bits relating to a pixel and we're flipping them to the opposite position along the x-axis, so affecting an Xflip. Now we do this 256 times. The L part of our HL memory address here is the source byte we want to flip, and the value we're writing here to that HL position is the result of that flip. And we use this later because by setting L to the byte we want to flip and then reading from the memory address HL, we can get the flipped equivalent very fast, or at least as fast as we can achieve. So that's what we're going to do. Okay, so that's the main things we want to look at here. The final thing I want to show you is the pattern data. Now MaxTile is generally speaking designed to be a 4-color tile system. Some systems I'm using 16 colors, but it's intended as a 4-color one. So that means that each of the tile patterns that we can select are 16 bytes. However, there is a special case, which is the fills. Now these actually use a pair of bytes, and so these are used for the solid fills. So we just repeatedly use a single pair of bytes to fill the entire tile. So here's our test data here. This is the main data. Then we've got our character data, the chibi code mascot at tile number 128. And so that's the calculation, say 16 bytes per tile for 128. That's the calculation for 256, and that's the calculation for 384. So if our source bitmap data doesn't align to the tile number we want it to, we can just space it out with some origins, and that's what I've done there. Okay, now just before we start looking at the tile drawing routine, let's see what actually calls it, and it's this code here. So this is the code that's doing the drawing of a tile map. This is covered already in the multi-platform series, the MaxTile series. We are backing up the stack pointer here. We're restoring it later on after the tiles have been drawn, a line of tiles has been drawn. So the stack pointer is available for us to use for stack misuse, which we will do. There is a check here, and this will switch us to an alternative version of the code. Remember I said that 4-pixel Y shift is not going to work well with our regular code because of the optimizations. This version will do that, and so that is just an alternative version there. This is just a slowdown for testing purposes. This is where the real magic starts. So MaxTile uses 2 bytes per tile, and that defines things like the program that's going to be used to draw the tile. It's the tile number itself, the pattern number that's going to be drawn at this location, and 1 bit is used as an update flag. If that bit is 1, the tile needs to be drawn. If that bit is 0, it's not going to be drawn, and this is because MaxTile, generally speaking, works with only a single screen buffer, and so it's not drawing everything every time and then flipping buffers. It's drawing only what needs to be drawn to update the screen. And so what we're doing here is we're taking the low byte of the 16-bit tile number, and we're shifting 1 bit out, and that is the update bit. The least significant bit is the update bit, and so we're shifting that out. And if the carry is set, we run the draw tile routine, and then we would move to our next tile. So this is what's going to this is what's going to actually transfer execution to our draw tile routine. I just thought it was important to see what had happened before our code that we're going to look at today takes control. Now, just before we look at the draw tile routine, what I'm going to do is we're going to have a look at the get screen pos routine. Now, this is used not by the drawing of the entire tile map, but by the drawing of the sprites. When we're drawing a sprite at a particular position, we need to calculate its VRAM destination to start the draw at the correct memory location. We have a get screen pos routine that does this. It's very similar to the previous ones I've used. This, like most of my newer code, works in logical units, which is a nice way of saying pairs of pixels. The X and Y coordinates of pairs of pixels works very nice on an 8-bit system, so that's why I'm doing that. Now, we've got some code here that is going to round the Y position to either a half tile or a full tile, just depending on if we've got that half tile shift code. We certainly can't do a 2-pixel shift, though. The code I've got here, it can't support it, so we're always rounding to at least half a tile here. That's what we're doing there. We're going to then store that in C here, and then what we're doing here is we are converting the X position into a tile number, and we're resetting the bottom bit here again as well. And so we can move in a half a tile, but we can't move the X position in quarter tiles because that would be 2 pixels, that would be half a byte, and that would be hell to pay for shifting all the bits. We'd have to have more lookup tables or incredibly slow code, so neither is appropriate for what this was supposed to do. Now, the way we calculate our VRAM destination is a bit of a pain, and this is again why the tile routines work so well when you're aligned to an 8-pixel grid, but not so well for 4 pixels. Basically, we take the top 5 bits here and we effectively multiply those by 64. So this is in multiples of 8 lines, if you will. The remaining 8 lines, 0 to 7 offset, or the Y position in lines from 0 to 7, well, we actually need to multiply that by 800, and that means to move down one line we need to add 800 in hexadecimal to our VRAM destination. But then when we go over that 8-pixel aligned boundary, as I say, if the tiles are neatly aligned, it's very easy, but if not, it's hard, because then we need to do something completely different, which is why, as I say, it's not so easy to do this. If you're allowing your objects to move in 4-pixel steps, or in even worse 2-pixel steps, you have to use far more difficult next line code to move down the VRAM on the screen. So anyway, bearing that in mind, what we're doing here is we're effectively multiplying the top 5 bits of the Y coordinate in lines at this point, and we are then storing that in the H part here. We've effectively multiplied by 64, we're storing it in H and L. What we're then doing is we're taking the bottom 3 bits, and we need that for our 4-pixel shift, and we're effectively going to multiply that by 8 here. And that's because we're going to write that into the high part of our pair. As I say, the Y line from 0 to 7 needs to be multiplied by 800 in hexadecimal, so that's what we're doing here by adding that to the high part. We're also adding the screen base, which is C000 by default, but if we're using double buffering, we would want to change that. And then we are adding the X position calculated in bytes. We converted that to bytes up here, so that is in bytes, and so we're adding that here. And that has calculated our VRAM destination. That will be executed when we're drawing the miniature sprites, before the draw tile map routine is actually executed. Before this routine is run, if we are drawing the entire screen, then generally speaking we actually use just the hard defined calculation of screen base here. If the tile map is being drawn on a pixel shift, though, that would have to be added to that, but we don't use the get screen pos function for that. Now, when it comes to drawing our tile map, what happens? Well, execution starts here at draw tile. Now, at this point, 1 bit has already been shifted out. The update bit is already gone from the value in the accumulator, and the reason for that is we need to set that back to 0 anyway when we draw the tile. So what we're doing here is we're checking the next bit, which was bit 1 and is now bit 0. Now, this is the program bit. Now, this works as basically a binary tree. The idea is that we want to have as few compares and conditions as possible before the most common draw, which is the unflipped draw, which is the vast majority of the background. Everything more complicated has is more and more subsets of branches till you get to that rarer use code. So what we're doing here is simply checking that program bit, and if that bit is a 1, then we're going to the advanced routine. Otherwise, we're going to drop straight into the basic routine. So in that case, we are then clearing the update bit by shifting a 0 into the byte and writing it back to the tilemap. What we're then going to do is we're going to add that to E. Now DE at this point is the source pattern data of our tile patterns. So we're basically calculating the offset within our pattern data for this tile. Now MaxTile uses 2 bytes and it's intended for 4 color tiles, and that means each tile is 16 bytes. Now by basically taking away the bottom nibble, and that is the program options, we've actually got an offset multiplied effectively by 16, and so this is very efficient for getting the source of the pattern data that we're going to shift into VRAM. So that is optimized for that, and that's why the bottom 4 bits are used for things other than the tile number. So we're then adding D and E to the 2 bytes. The first byte we loaded here, and the second byte is entirely the tile number. So we're loading that. That's our 16-bit offset to DE, the source pattern data, and we then transfer that to the stack pointer. We're going to use stack misuse. So what we're going to do now is we're shifting to the shadow registers. Now when this is executed, BC points to the tilemap, DE points to the bitmap data, and HL in the shadow registers is the VRAM destination. So what we're now going to do is we're going to write into the VRAM for this tile. So basically we're going to need to move down a line repeatedly, and to do this we add 8 to the high part of the HL pair, 800 for each line down within that 8 pixel aligned boundary. And so what we're going to do to achieve this is we are going to first back up the H part. We need to return with the HL pair the same as it was when it started. So we're backing up the H part. We're loading the C register with 8 because we're going to repeatedly add 800 to the HL pair. And so what we're then doing is we're popping 2 bytes from our source bitmap data. We're going to transfer the first byte, E. We're then going to move across the screen by inking L. We're then going to write the D byte, and then we're going to move down. We add C to the accumulator which contained H, and we then write the accumulator back to H. So HL has now been moved down a line, but we're now still on the right hand side of the tile. So this time, instead of writing E then D and inking L, what we're doing this time is we're doing in reverse, D and E and decrementing L, and we're effectively doing a zigzag down the tile, and that's saving a few shifts. If we were moving back at the end of each line, we'd be wasting time, so we're not going to do that. And you can see here, each time we're updating the H part of the HL pair to move down a line, we just add C to the accumulator and transfer the accumulator back to H. And to my knowledge, that's the best way of moving around a tile. Now at the end of this tile, basically L has ended up the same place as it started because we've zigzagged like this. We've just ended up back on the left hand side, and so all we need to do is move H back to the start of the tile, and to do that we simply transfer the backup we made up here in B back into the H register, and then we return. Now the rest of the code, if you've seen the rest of the tutorials on the MaxTile series, but the rest of the code has platform specific code to move across the screen after a tile's been done and down the screen after a line has been done. So that is not that's not a requirement on this part of the code, so that's why you don't see anything to move across or down the screen. This code is just responsible for drawing a single tile and leaving the HL VRAM destination the same as it was at the start. So that's the basic template for an unflipped simple tile. Now, if it's not an unflipped simple tile, this advanced code is called, and what this is doing here is it's checking the X and Y flip bits, which are currently bits 1 and 2, but they were actually 2 and 3 before, but we bit shifted across 1 because of moving the update bit out before this routine was executed. Now, if both of these are 0, then we shift into the secondary part of the code, which we'll look at next time, which is known as the custom programs. If one of those bits isn't 0, then we're either X flipping or Y flipping or X and Y flipping, and that's what we're going to look at now. Okay, so at this point we've basically decided we're doing some kind of flip, and so what we're doing here is we are resetting that update bit once again in the source tilemap to mark it as updated, and then what we're going to do next is we're going to actually calculate the source tilemap address of our data. So like before, we're loading in the HL pair, adding D and E, which is our source pattern data, and moving that into the stack pointer. Now again, it's important to notice that we're using the same pattern data whether we're flipped or not. The CPC version has real-time conversion code for Xflipping and Y-flipping the data, and so only one set of data saves memory, and so that's a good thing. So we've calculated that source address here because it's going to be the same no matter what. What we're then doing here is we're seeing if the Y-flip flag is set within the source value, and if it is, we're jumping to the Y-flip code. Otherwise, we're using the Xflip code. Now, the Xflip code basically works like this. We load the BC pair with the the lookup table for the flipping that we defined before, and then we read a byte from our stack. We pop some bytes. Those are our source pattern data. We use each one as a lookup in that lookup table, read the byte out, and then write that to the screen. And we then just draw it to the screen in the same way as before. Unfortunately, though, moving down the screen isn't as efficient now. Before we were relying on the accumulator containing the H register. Now it can't, because we're using the accumulator for other things, and we can't use the C register for the value 8 because it's being used for other things. So we're adding 8. We're doing this less efficient version here, but it's okay. It's better than having a second copy of all the Xflipped bitmap data, the bitmap pattern data. We can spare the CPU pair as long as we're not flipping every tile on the screen. So hopefully we won't be. Anyway, we pop 2 bytes of our pattern data, 1 line's worth of data here. We load the C part with the D part that we want to flip. The B and the BC pair has been defined as the top byte of our lookup table. Now, when we read from that lookup table, that is the flipped equivalent of the byte that was put into C, the D part that we wanted to flip. And now we just write that to the screen, move across the screen, set C to the E part, read in and write that to the screen. We've now flipped an entire line, so we move down a line. And we do the same as before. It's the same kind of template as the simple version. It's just everything's going via the lookup table, and the move down line routines are more complicated, so a little bit slower. And at the end, we're backing up by recalculating our H part, because once again, that we were using the B register before to store the backup. It's not available to us anymore. But apart from that, mostly the same. Now the Y-flip routine, that's actually easier. Basically, we read in the source pattern data in the same order, and we write it to the screen from the bottom and move upwards. So we're reading the source data in the same way, drawing it backwards on the screen. Works perfectly fine. So that's what we're doing here. The first thing we're doing, though, is we're checking if the Xflip bit is set. We've already decided the Y-flip bit is set. So if the Xflip bit is also set, we're X and Y flipping. Otherwise, we're just Y flipping. So Y flipping, we move to the bottom of the tile, the last line, and that's what we're calculating here. And then what we're basically going to do is we're going to draw the unflipped data. We're not using the Xflip, we're just doing the Y-flip. And so we're reading in the data as we did before with the unflipped version. We're just subtracting C from the high part of the HLVRAM destination each time. And that is moving us up the screen rather than down the screen. Apart from that, basically the same code. And at the end, we're restoring the H register in the same way as before. So drawing to the screen backwards, reading in the same way. So no, it's pretty efficient. Certainly a lot better than storing extra pattern data. The final version is the XY flip, and that uses both tricks. So we're going to draw up the screen, and we're going to read in the data and flip it via the Xflip lookup table. So we are calculating the last line of our VRAM destination here. We are setting our BC pair to our source Xflip lookup table, and we're reading in our bytes from our stack misuse. We're reading in the pattern data, and we're flipping it, and we're writing it to the screen, and then we're going up the screen. Again, we don't have enough registers to have a more efficient Y move routine, but this will suffice. So that's what we're doing. We're moving up the screen here, and that is how I've forgotten to update the comments here. It should be move up the upper line. I'll get that fixed. But anyway, that is how we are X and Y flipping simultaneously. And as I say, I think that's really a good thing. Now, the one thing I would sort of say about MaxTile is it isn't lightning fast. Lightning fast is very hard to do on a system like the Amstrad CPC on a Z80 system with a large screen. It achieved what I hoped it would. It's reasonably it's reasonably adequate for most purposes, and as I say, it does have a few really good benefits. As I say, it's multi-platform. It can work on a lot of different systems in virtually the same way. The end code that actually calls MaxTile works in the same way on all the systems. It's just the platform specific parts that need tweaking. 8x8 tiles are very efficient on most systems. There's a few things like the Neo Geo, which uses 16x16 sprites. Not so much on that one, but you're always going to have outliers. You have to work with one primary system, a few other systems you'd like to work with, and if you can suck in other systems that are fairly similar, then you do so. And so that's what I've done with this code. The intention is that MaxTile would be used as the foundation for any games that I write in the future. That the functionality I've given it is functionality I wanted for other games. But it is important to say that if you were trying to do the fastest sprites possible, having optimized routines that draw much bigger sprites, if that's what you need, is going to work better. And if you don't need the cropping, because those sprites never leave the screen, like the Chibi Akima's game, the Chibico mascot, the player's character could never leave the screen, never needed clipping. Any code that provides that functionality is going to be less efficient. And as I say, MaxTile is designed where a double buffer is not available. If you have a double buffer available and you've got other things that mean your drawing routines are more efficient than these ones, like again Chibi Akima's, the bitmap gradient draw was a hard-coded piece of code that only drew that. No code that you put in a subroutine of tile drawing is ever going to beat that or even compete with it for speed. So it all depends on your requirements. But as I say, this is a good all-rounder, simple, multi-platform software and in some cases hardware tilemap. Anyway, go to the website, download the source code, the build scripts, use it any way you can. Use all of it if you can, if you want. If you can't, but you want to take little bits of it out, take them out, use them in anything you can, even if they're commercial. You're welcome to do so. That's what it's there for. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.